Good morning. Today, we explore dynamic planning for motion control, a core technology enabling intelligent motion and high dynamic systems such as robotics, autonomous vehicles, drones, and automated industrial equipment. This field addresses a fundamental challenge. How can a system autonomously plan and execute desired motions while respecting its own physical limits and environmental constraints? Unlike traditional approaches that separate path planning from control, dynamic planning integrates system dynamics directly into the planning stage. This ensures the generated trajectory is not only geometrically feasible but also dynamically executable, leading to more efficient, robust, and high-performance autonomous behavior across advanced engineering applications. Let's break down the key concepts. Motion control focuses on low-level execution, how to accurately track a given desired trajectory or command, such as position or velocity. Dynamics describes the motion laws of a system under forces and torques, considering mass, inertia, friction, and other physical factors. It answers, how much force is needed to produce a certain motion? Planning generates a path or trajectory from start to goal under given constraints, deciding which route to take and at what speed. Dynamic planning deeply integrates all three. It explicitly uses the system's dynamic model during planning, ensuring the resulting trajectory is physically feasible and can be directly used for precise control, bridging high-level intent with low-level actuation. The first step in dynamic planning is modeling. We must establish a mathematical dynamic model of the system. A common form is, additionally, we must model constraints such as actuator limits, maximum torque, speed, and environmental factors like obstacles. An accurate model is essential. It forms the basis for all subsequent planning and control. A mathematical dynamic model of the system. This is the core of dynamic planning. The goal is to generate a time-parameterized trajectory QD that satisfies dynamic constraints, avoids obstacles, and meets performance objectives. We distinguish between a path spatial geometry only and a trajectory includes timing, velocity, acceleration. Common methods include optimization-based approaches, where we formulate planning as minimizing time, energy, or jerk subject to dynamic equations and constraints. Differential flatness simplifies planning for certain systems by reducing optimization dimensionality. Model predictive control MPC performs online receding horizon optimization, enabling real-time adaptation. Each method balances optimality with computational cost. Once a feasible trajectory QDT is planned, it is sent to the motion controller, which computes the required forces torques to make the physical system track it. Techniques include feedback linearization, which uses the dynamic model to transform the nonlinear system into a linear one for control. Computed torque control is a specific form that actively cancels nonlinear dynamics. Impedance admittance control is used in interactive tasks, regulating desired dynamic behavior like stiffness and damping during contact. The controller ensures the planned trajectory is accurately executed on the real hardware, closing the loop from planning to action. Several challenges remain. Real-time performance is difficult due to nonlinear dynamics and high computational cost. Uncertainty from model inaccuracies and external disturbances affects reliability. High dimensionality in multi-robot systems adds complexity. Current trends focus on integrating machine learning, such as deep reinforcement learning, to learn policies or accelerate optimization. Efficient real-time solvers, e.g., OSCP, ACADOs are being developed. The field is moving toward tighter integration of planning and control, leveraging data-driven methods to handle complexity and uncertainty more effectively in dynamic environments. In summary, dynamic planning for motion control represents a complete technological chain, from task goal to trajectory planning considering dynamics and environment, to feasible desired trajectory, to model-based control, to actuator torque, to physical motion. It marks an evolution from the traditional plan first, track later approach to an integrated, optimization-driven paradigm where planning and control are deeply coupled. This integration is key to achieving high-performance, adaptive, and intelligent motion in applications ranging from industrial robotics and CNC machines to autonomous vehicles and aerospace systems. This is the end of MCTV Training Class 17. Thank you for your watching.